everyone. Welcome to this session by Peter Saxton. So it's titled EYG, a predictable and useful programming language. We're glad, Peter, that you could join us today.
All right, thanks. Good morning, everyone, or good morning from here. Let me just go to share my screen. Okay, so so the title I've got here is slightly different. It's Eat Your Greens, a philosophy for language design. So if you hadn't read into it, this is the punchline for EYG. So right, let's get started. So this is me. I'm Peter Saxton. Thanks for the introduction. I'm crowd hailer on the internet. And I'm currently actually working full-time on making this language, having previously spent 3 years doing Go for manufacturing. So let's get going. So predictable and useful. Why these words? And let's just do the definitions. It can't be a talk without a good clarification of definitions. So predictable, ability to be predicted. So that's not very useful. And the only other thing that Google gives us is this derogatory version, which is always behaving or occurring in the way expected, which to me sounds very sensible and not at all derogatory at all. This is exactly what I would like my programs to do. Certainly occurring in the way expected isn't saying even always in the same way. So that's nice. And then we have useful. Useful, I think we understand what useful is. It means to be practical. It also potentially means to be used in several ways, which is widely applicable. And again, I didn't set this up, but the first simile is functional. So that's nice. So so predictable. In a programming language, we might consider this no undefined behavior. I mean, never crash, although obviously you could predictably crash. This one's slightly more controversial, but same answer every time. That would mean deterministic. We don't necessarily need to go that far, but it's something to bear in mind. Useful, okay, so it's we can build the required applications and potentially useful in several ways. But I add here, well, which ones? There's the right tool for the job kind of question. So I think one of the most important things for applicability to usefulness is scale. I think this is probably where most flame wars erupt, where people they're talking about different size teams or different size projects and kind of going which language is best. Okay, I mean, there's a programming problem space, which is small enough, education and examples, that maybe Scratch is the best example, like genuinely the best language, and C++ would be terrible. Vice versa, the idea of building a browser in Scratch or an operating system in Scratch is totally untenable. So I have a few kind of thoughts on where these things should be. I've put this large selection for apps. I think apps go all the way from, 2 people making a web app to, huge enterprise apps where Java excels. And then just to sort of highlight like where I want EYG to be and what I'm going to be talking about is big scripts to small apps, 1 to 10 developers, as just a kind of what I optimize for, what I think about. And it's also what I'm familiar with, having done several startups. So how do we rate language features? The existing languages have already had to make decisions on how they choose between predictability and usability. And so here we have, again, my opinions on where a lot of these things would go. So let's pick a few key ones here. So we've got predictable towards the top, we've got useful towards the right. And I think this kind of off diagonal from top left to bottom right is actually quite interesting and where we talk about a lot. So if something is predictable but constrained, but less useful, then it's constraining, and that's fairly easy to manage. Like if you make the rules tighter, you can get more predictability. And on the other end, if you make the rules looser, you can just write assembly by hand. It's obviously maximally powerful, but its usefulness, it's maximally useful, but it's potentially totally unpredictable. So, we have a classic memory management. Manual memory management for high power programs is sometimes not optional. Like you can use a manual language C potentially everywhere. So it's applicable in all places, but its predictability is low. Maybe let's clarify slightly. Here, predictability, or to me, is sort of close to intuition. Obviously, if you have a deterministic language, then it's 100% predictable by that measure. And if you have something that's Turing complete, then they're all equally useful. But I think that we can lean to intuition and the definition of sort of expected. If you look at a big wall of C, you'll have less intuition. It takes you longer to work out from a human's point of view what you expect it to do. So, that covers this cross diagonal. I put type systems over here as just less than useful, not because I think that they aren't useful kind of in the long run, but a lot of their use comes from predictability. And if we're being truly kind of precise in our language, just adding types where you have to annotate only actually constrain the things that you can do. They don't bring your program to more applications. Potentially, there's probably with all of these things enough. It depends that we can argue about a lot of. But once you have something which is less useful but predictable, you can then build on it. So if you have to add your own type annotations, type inference makes it slightly more useful. You don't lose anything, but it doesn't cost you so much. And then on top of this, we can build further tools. So for example, autocomplete in your language server doesn't change anything about the predictability, but you're allowed to use the foundations underneath it to get more out of it. And so yeah, we have these ones down the bottom where we have mostly, I guess, misguided things. And then up onto the right, we have what we want. So this is what I'm going to talk about: algebraic effects, closure serialization, and REPLs. Obviously, I've put them here because I want them to look good up here. But REPLs pretty much always where you start. Well, if you consider REPLs and shells, like Bash is a REPL for the Bash language. Algebraic effects, I think, are a empowerment of IO monad to do notation. I think this is strictly true. They are technically free monads, which means they have more application. And then closure serialization, which is the one we'll talk about last. So we'll get to that later. So when you're picking features to put on this space, you need a philosophy. And here we have a lot of vegetables, which leads on to the idea of eat your greens. So eat your greens is a thing that I was told all the time, even if it wasn't about vegetables. Beyond diet, eat your greens can symbolize doing things that are good for you, even if they are not immediately enjoyable or easy. So who likes types? So I can't see the room, so I'm going to assume you've all got your hands up. It doesn't matter what kind of type. They can be static, they can be strong, they can be gradual. But yeah, did you appreciate them the first day you were coding? And I would argue that for a lot of people, the answer is no. And the reason is types don't add anything to the smallest programs. You expect to get value from them later on as the program evolves, as it gets larger, as more people are involved. I would argue that types and type systems really are not, they're not sugary and quick reward. Once you're a sort of seasoned programmer, you can start appreciating a nice type system. But in your learning process, it's not likely that on day one you want to explain what these are. So types make things harder. Structured I/O, having to deal with the I/O monad is potentially harder than just that inline print statement from Python. A classic one I really, frustrated with is JSON deserialization. Your untyped object comes off the wire and you have to write your decoder potentially, or you have to increase the complexity of kind of inferring decoders. You have to declare stuff up front, which is what I've put object creation here. Like if you want a custom type, you don't get to start using it. You have to define it and declare it. So yeah, again, I'm saying the compounding value over time. That's what types are good for. So now we go back to this same kind of selection of things, and I've changed the axes around here. So I think we have this off diagonal here, which is abstraction to indirection. And this is what we want, right? Abstractions, we talk about abstractions all the time, and when abstractions go bad, they become sort of indirection. But there's also this kind of, then we now have the other one. So we can start from a math side or an engineering side. So, on the C is all the things you need to get your computer. You've got such a high power problem, or you're just starting from the machine, or you've got your computer for the first time. You're just like, let's just put everything that it can do in the language. And then on the other side here, you can start with a lambda calculus, maximally constrained, still can do all of Turing, but can't actually talk to your computer. And then we have the more real world languages. So ML has more theoretical foundations, and over time you try and add things that make them more applicable, more useful. So we go up to like Gleam and OCaml. And finally, another approach. We have Gall's law. A complex system that works is invariably found to have evolved from a simple system that worked. So basically you're saying that simple systems built up are easier to work with than a complex system designed from scratch. The way I take this, and this is a sort of the philosophy of Eat Your Greens, is I want to start with things which are as predictable as possible and try to make them applicable, rather than giving you everything, giving you all the powerful features, because constraining powerful features is much harder than extending predictable features. So what we have here, if you can see them, these are milk chocolate sprouts. We're not going to sugar things. Eat your greens is we need to deal with the vegetables and see what we can get from it. And this is the final argument for why. So Moore's law, and my argument, moves things towards the more useful axis. As computing power gets higher, you end up with, say, half the programs that need manual memory management because your computer is more powerful. Or the other way of phrasing that is twice the programs can afford the abstractions that the mathematical approach starts from. So, it's a perennial argument between the cost of abstractions. Obviously, Rust tries to do things zero cost, and there's always going to be a fraction of programs that need it. But due to increasing computer performance, it will be less and less over time, by my argument. So this brings us to EYG, the language. So the language is statically typed, structurally typed. The type system is totally sound. We have algebraic effects, which are a complete control of side effects, closure serialization, and a strongly typed REPL. So these are all, there's no we don't drop them in any way. We don't compromise them. We're very puritanical on all of these things, and we hope to have increasing value. Once we've eaten all our vegetables, we get more power later. So yeah, the last two here, they're both interesting, but they're not time for them in this talk. Okay, so EYG is statically typed. So here's your first piece of EYG code. Hope it looks reasonably familiar. And statically typed means it's typed ahead of time. So we can click through this code here, and we can go, yeah, this is a string, it needs to be a number. So we go, make it 100. And he goes, yep, missing the variable sum. So we click over here. We can use the type system to give us help in the editor. So we click our var, and it goes, these two exist. And we have the total, 110. Very nice. It's structurally typed. So this is important so that you don't have to ever declare a type up front. So we have these Alice and Bob records. Alice also has an age field, Bob does not. So they're not the same type themselves. But when we have this greet function here, this greet function takes anything. So it destructures. This is destructuring in the function head. And we're going to append the string hello to the name. So this requires it to be a string value itself. And then we alert it. So if we run this, we get hello, Bob. And we can pass in down here the value Alice just as well. So we click and run this, and we get hello, Alice. So structurally typed. So these, I hope, are familiar to a lot of people. Soundly typed just means that everything, like every option, every path is taken care of. There is no way to forget something. So here we say we've got this missing row in this match statement for greater than. So if we put one in, oops. Okay, so it turns out that M means mirror in the, the slide software here. So we won't do that one. But yes, we can put a greater than in here. And yeah, and then finally, so EYG is a browser native runtime. So I've kind of been just showing you this editor. So we have this structural editor, and we have this runtime that exists in the slides. And so we should be able to go, for example, here. Hi, everyone. I'm presenting at Functional Conf 2025. And so we can say yes to this. And so there's an effect in the runtime, which we will get around to, saying there's a tweet effect. So if we authorize this app, this should go away. Did this all from the slides. It's quite slow dealing with this, but yeah, apparently that tweet has been sent from my slides. So we can go and find that later. So algebraic effects, there you go. You got your first introduction to one. Algebraic effects represent all impure behavior. So IO is the sort of maybe classic example, but this applies for things like random, time, exceptions, concurrency, and mutability as well. There's another talk, I believe, in this afternoon about algebraic effects, so you can hear someone else talk about them as well. I think they're very interesting. So to explain what algebraic effects are, we need to be clear about what a function is. So a function is the relation between a set of inputs and a set of outputs. So every set of inputs has exactly one output. So we have a simple one argument function where we uppercase. for every input, there is a known output, and subtract, where for every 2 inputs, there is a known output. Functions compose, so we can have this my function here, which takes 1 argument and returns 1 value, and it's always going to subtract 5 and take the absolute value. And again, should be familiar to sort of people at the functional conf, but functions can be values. So we have this each function where it takes a list of strings and an operator function, this uppercase. So we end up with a list of uppercase functions. So then we get to these boxes. Now, you might look at these boxes and go, they look sensible, but they actually can't be functions, because the definition of the function, if you remember, was that for every input, there's an exactly known output. So, well, let's look at the print example first. We could write a print function that took any string and always returned an empty record, but it wouldn't do anything. Like, it would just return the empty record. And then the random one, which looks, what's it actually doing to the outside world? Well, if it had the same answer for every input, then it would always have to be the number 4. So this is the classic XKCD, if you know this, which is, you can choose it by a random dice roll ahead of time, but this get random number is not probably doing what you want. So side effects depend on the whole world. Nothing in the program can actually know the limit of what the side effects do. So here we have, the whole world. So you need to talk to the world outside to get a random number. And the whole world has nasty things, including, launch the missiles, which is a bit of a riff on, what effects might do. And it's also a way of saying that, effects are not reversible and, can have permanent impact. So how are we going to deal with these? So first thing I want to introduce very quickly is continuations. So continuations is just another type of function. It's a first-class function. And the idea with a continuation is, instead of returning values, you take the rest of the program, which is what we represent here, as a third argument or a last argument. So instead of taking 2 values and returning the number to this negate function, we take the negate function, or the negate function and more, as the rest of the program. We pass it to add k, which means add continuation, and it will call it with the result of adding those numbers together. So programs perform effects with the remaining program captured as a continuation. So instead of a random function, we have a function called perform that is going to perform random. And we take the argument. So random doesn't need any values, but we'll just pass in a single value, because perform is always going to take a value, a label, and then the rest of the program. Okay, so that's what we're showing here. And then we get this value. So this program is totally pure. It takes values, it returns a value. It actually takes just this one value, if we consider this is written in the program. And the single return value is this object, which is the label, the value, and the resume function. And then this is taken away and passed to the outside world, which will do whatever it wants with it. But the key point is the resume part, or the rest of the program, is a separate program, if you will, or a separate part of the program. So the outside world calls resume by calling that continuation with the value you get. But because it's a value and it's been sort of reified, you can call it more than once. So you can pass in 4 and you get 5, but it also would work to pass in 10 and 11. And you can do a lot of things with this. So we'll do this quite quickly, but the reason effects are valuable is that they can be inferred. So if we were, for example, to make a function called f, we're going to make it take the now effect, for example, and do this. Let's make another one. So we'll make a function called g, which will take the alert effect, where we're going to put up a string, and it's going to, yes. So I've actually made a mistake on f, so we'll come around to that. So this needs to be m. We need to pass in m. We need to make f be a function, sorry, which is what I missed here. And then we'll make it perform now. And record that. Okay, so now these are in scope. So f is a function that takes something. These numbers mean we are not yet specified, and raises the now effect with unit, returns something we don't know, and returns it. So the interesting point here is the return value from now is going to be the return type here. And then we have over here, we have the zeros match and the ones match. Okay, so we're not going to do anything with those yet, but we can make another function, which would be equals h, which would be a function which we're going to call nothing with. And what it does is we're going to get the now time. So we're going to do f, which is the now. And we're going to pass it to the alert function. So we're going to put it to G. And if we now view all the things that are in scope, here we can see that H raises 2 effects. Okay. This is, I mean, we'll get into the details of what's going on in the shell here, but this is the best way to kind of see this building up over time. And maybe just to show that it works, we'll call it. So if we call H with a record, we now run it with the time that we have right now. So this is 7:23 in the morning for me here. Right, crack on. I think I'm running a bit on time, so I'm going to skip over capturing effects, but leave it to say that there's a way to essentially unify all test mocking is my best way of thinking about them. So we have a program where we take a flip effect. Yeah, I said I wasn't going to talk about this. You can ask me afterwards. So closure serialization. So I would, if you were all in the room, ask you to put your hands up who'd heard of this, but it's the process of converting a closure into a format that can be stored or transmitted. So I think, again, the phrase closure is reasonably familiar to the functional audience. So we have this F here, this F function, which takes an X argument, but it also captures the bump argument from the environment. And then so what we have here is we have this built-in called capture, which is returning the AST, but it's an AST that makes the function. And we can see that it's set up bump, but we can't really see into this very well. But if we change this to serialize, we get this JSON value, which is actually how the program, the EYG program, is stored. So if we copy it and we come over here and we paste it, we end up getting a function that represents what we serialized. And the key thing to note here is we lose the message. The message is not used in this function, so it's not captured as part of the environment that this function uses. Okay, fair enough. So yeah, why is this so interesting? Well, serialized code can be transpiled. So why is this interesting? So here we have the same F function. If we press J here, which is going to give you the built-ins, we have this to JavaScript one. And then this takes one more argument. So we need to put an argument in afterwards. We need to pass a number. So this will be, let's say, 3. Oh, no. Yeah. Pardon me. I think my escaping for this has broken. We've jumped to a random slide. We've jumped to the 3rd slide is what we've actually done. But yeah, so serialized code can be transpiled. So this is the JavaScript version of the closure that we captured, noting that the bump value is called bump 110, but the message value here is not. So this allows you to have a program that runs essentially during build time. So the use of message and that is build time, but then the return to JavaScript becomes the runtime. So yes, effects and closure serialization are very powerful because we now have 2 environments that this one program is running in. And so is closure serialization possible in other languages? If you've not seen it, the answer is yes. The long answer is, I mean, yes, still, but it's complicated. Yeah, this is, I do not expect you to read this, but there's Pulumi have this really nice ability where you can create lambdas from a runtime, a JavaScript closure, but it takes 1,600 lines of code for them to make this work. And they have to repass it, walk the whole object tree, and it's exciting. So yeah, so why do closure serialization? So I argue that programs run in a lot of places. So your developer laptop could have this function. You could have a system here, which takes a config, which comes from the build server, request that comes from the application server, and some client or DOM information that comes from the browser. So if we change this, so I think this should actually be window, that would be better. So let's make this window. And we say yes. So now we can call this with a single argument. So it'll automatically give me 3 because it knows the type. So if we call this with some configuration, we get a new function that takes requests. So this is just currying. All right, cracking on. Let's use this. So this is probably one of the 2 larger code examples I have for EYG. So what I'm trying to show here is that we have a program that has a build context, and it also has the sort of app context that it runs in. And so the the interesting thing, or well, the key thing here is we're going to download some built application afterwards. So my app is something that takes first argument, which is the information at runtime, and then it takes the DOM or the window or the web, which we're going to ignore. So what we do is we then alert a message here. So we have this, we're going to alert I was created at. So this is an effect that's performed in the client. And this time comes from the build configuration. And the build configuration was passed in at build time here when we performed this now effect. So if we run this, if we click to run, we get the now performed and we get the download. And so up here, let's see what this does with full screen. We have an index.html file that says I was created at 7:28 UTC. But the now was run in the first place. So I think we need to, right, we've got a full screen of nothing. We need to get out of that one. We need to come back here. That's me. Back over here and full screen again. Okay. And so what we've done here is we've got, again, we're making use of the kind of web environment that we live in. We can take the same program, which is the my app here. We can build it with the same build function. But instead of downloading it, we could actually use another effect, which is available, which I've built into this web runtime, which would be deploy the site to Netlify. Now, I've not actually kept the Netlify URL, so we can believe me that this will run, but I'm not actually going to go to that page and see it. So yeah, let's crack on. So I don't know how much time we'll have for this one, but I think the key point about closure serialization is I want to take single programs. I want to make multiple parts of the stack a single program. And the very first part of the stack is actually the REPL or the shell, which can also be typed, which is what I showed you here earlier. So, okay, maybe I won't do, well, we'll do a quick example with this. So we can have, for example, we can say if something is equal. So we can do, interesting. Okay, so I can't get here without the, yeah, let's do it. Standard library. We get something to be equal. We call it, and this is just off the bottom of the screen. Why is this? Okay, the thing I wanted to show was that inside the REPL, we can type this and it'll automatically give us that something is true or false. But we can undo that, put a value in. So we can say, let's not do a number because that causes trouble. A, we can do A again. We need to set this to a value, so equals X, and run this. So why do we want to type the shell, and why is this interesting? Because we can do partial type checking. So if we press this V here, this X value, we know it's a type of true. It's been actually refined in the shell. Okay, that's kind of the main thing. I'm not going to show a val right now. That's going to need more sophisticated examples than I can probably quickly type out into the shell. But yeah, so the types are refined is the key thing. And the other thing was type checking is optional. So because you're writing the code and immediately using the code, you can have the same, you get the same error from the runtime as the type checking. And because you're only using the code once in a REPL or in a build script, if you don't hit an error, which the type system might find, it doesn't matter because it's not early warning if you're using the code immediately as you create it. Okay. So structural or nominal typing. So this all requires typing to be structural. So nominal typing is when you have to define names up front. So this Java class here, it has a name field, but it's called person. So if you need a function, it has to explicitly take a person. TypeScript, you have a very similar looking thing. You have this interface called person, but it's defined by the content it has. So any function that takes a name of a string can accept a person or any other interface with that field. Whereas if you had something that looked exactly the same, so if you had a user class in Java, it would not be acceptable. And so, you know, nominal types, you have that type declaration up front. So I'm starting from the bottom here just to confuse us all. But nominal types also have a bounded validity. Like the name person means something for only a certain scope, which is probably the project. And it also means that the types don't last multiple migrations. They are, you know, if you recompile the program later, or if you edit a person and add a new field, then it's obviously not the same person. And the system doesn't have any connection between the old and the new version. Whereas the nice thing about structural types is because there's no human meaning added to them, you can have two programs written at different times, and if they both have the name field, you can consider them as both satisfying the sort of global has name interface. Okay, so this is eat your greens. This is kind of working on the theory that if I start with a very simple and predictable type system, I can get more value by leveraging it everywhere. This is where I sort of level up, rather than adding sugar to it or kind of having more interesting features that limit it self. I say limit it to a single application. Like I think applying a very small set of rules to a very wide scope is more interesting than adding lots of rules. And so I want to eat your greens to extend to your development environment or your CI environment. Like it's already interesting that I have an environment for working in slides, which is interesting to me. So yeah, so a singly typed program should extend over the whole stack. I want to keep working on this to deal with stuff like database queries, infra provisioning, tackle that problem that Pulumi or Terraform are tackling. Service workers are also an interesting untyped space. If you do much front-end work, like your main thread and your service worker thread speak through untyped messages and actually need two JavaScript files, so it's not a single program. Yeah, and basically everywhere you can think of, I'm interested in doing that. I think that we don't have more time, and I haven't seen the questions, so I'm going to go and have a look at those. But yeah, so this also works for hot code reloading, which is a fun demo, but it takes a bit of setup. So yeah, so any questions? And you can find more about Eat Your Greens at eyg.run. And the main way of keeping up to date with information is to join the mailing list. So yeah, thank you if you've been listening. Thanks for having me. That was fun to do, and I hope to I'll see you all in the Hangout.